So now that we understand how to model heat transfer in simplified systems, let's try to see if we can't use the information that we get from those models. That is the way that the heat transfer rate depends on geometric and material properties of those simplified systems. Let's see if we can't use that information to try to understand how objects that are designed to optimize heat transfer between two things are designed, right? And so in order to do this, I decided to bring in a little prop for show and tell. And that prop is a very common device in the study of heat transfer, which is a heat exchanger. Now, this thing, I hope the glare doesn't catch it, but it's a very, very simple thing, at least on its surface. All it is a set of inlets that take in a hot liquid and a cold liquid, and just some geometry on the inside that takes the hot liquid and the cold liquid from one end of this device to the other. And so you expect to have hot liquid and cold liquid coming in. You have both of them coming out. Now there's a tube structure inside of this that prevents those two liquids from mixing. So, you don't get some like sloshy mix of both of them at the outlets. You actually just get hot liquid and cold liquid. But the thing is that because, the laws, or at least the empirical observation of heat transfer are true, we know that that hot liquid and cold liquid are going to be in thermal contact inside of this thing, right? Even if there is like some kind of like metal sliver or layer or whatever that's separating both of them. And so the point is that both of these liquids are in thermal contact with each other. And so the hot liquid is going to get colder as it flows from one side of the device to the other, and the cold liquid is going to get hotter as it flows from one side of the device to the other. And heat exchangers are usually designed, true to the name, to optimize this heat transfer, right? You want to maximize the amount of heat that's being transferred from the hot liquid to the cold liquid. Okay, so now I want to ask you, what do you think the inside of this thing looks like? All right, so like this is a very simple device at its start. You can see the outlets. There's no power source even. This is like passively powered, so to speak. And so I want to ask you, there is a separation between the hot and the cold liquid in here. So there's got to be like at least two chambers through which this thing flows. What do you think the inside looks like? And I'm going to show you how, because I cut it open. And at the end of the lecture, we're going to see whether or not the prediction that we make about what this looks like based off the simplified models of heat transfer that we've developed so far, we're going to see whether or not that matches, right? That prediction matches to what this actually looks like. So how could this look like? What's a potential guess? So let's make a sketch where we're looking at this from a front view. Okay, so there we go. We're just going to sketch it like this. And this just looks like a nice little rectangle. That little rectangle, we can sketch in the following form. And we can ask ourselves, where's the hot liquid and where's the cold liquid? So here's a very simple kind of way to think about what this could be. This could just maybe be like a single separating, piece of metal. And then the hot liquid flows on the top and the cold liquid flows on the bottom. Or something like that, right? We could separate it vertically too. It doesn't matter very much. And then we can ask ourselves, well, if we assume the standard assumptions for heat transfer, or for simplified heat transfer, I should say, then we can try to see what this would look like if we model it as a thermal circuit, right? As a thermal network. So what does this look like? Well, we have liquid in contact with an object, a solid object, which is this separating thing. And then this separating thing, which has some pretty small, thickness, is also connected to this cold liquid over here. And so from the perspective of, thermal circuit modeling, this basically looks like a series thermal circuit where we have a convective resistance here. We have a conductive resistance over here. And we have another convective resistance here. And so the point is supposed to be that these are representing the liquids themselves, and this is supposed to be representing, the little sliver. Now here's the interesting thing, right? If we want to maximize heat transfer through this thermal circuit, what are the geometric parameters that I can manipulate in order to try to minimize the thermal resistances of all of these elements? Well, the first thing is that if I can make this thickness as close as possible to 0, I bring down the conductive thermal resistance in the middle and therefore increase the heat transfer rate that I see as a function of the operating parameters of the heat exchanger, right? So if I am able to decrease this thickness, I decrease the thermal resistance and enhance heat transfer. And so we want this sliver over here, not just for the perspective of, simplifying the analysis, but we want it from the perspective of design to be small, okay? So it's justified that we draw it as this tiny line, okay? In fact, we're gonna almost always assume that this thickness is so tiny that this resistance basically doesn't exist. But here's the other thing. Notice that for all of them, the thermal resistance is inversely proportional to the surface area over which the heat transfer takes place. What is that surface area? Well, it's whatever the surface area of this little rectangle, the separating element is, right? So whatever the dimensions of that little plate are, then that will be that surface area. And the bigger we make it, the smaller the thermal resistances are going to be. So, if you just think about this at face value, that might lead you to say, oh, well, then why don't we just make a heat exchanger really large? Right? That will enhance heat transfer. And yes, that's true. That will work. But clearly there has to be some kind of other thing that we can do in order to enhance the design of heat exchangers because of the fact that the heat exchanger that I just showed you is super small, right? Like, how on earth is this device supposed to be efficient if the area of this single plate that is hypothetically in here, that area would be very, very small? Like, why wouldn't this be 3 or 5 times larger? The answer is interesting. Let's try another thing, right? So remember that the idea is that this is supposed to be a surface area over which the heat is transferred from hot to cold liquid. So instead of having a single plate with 2 liquid chambers, why don't I have 3 separating plates and 4 liquid chambers? Why don't I do something like this? 1, 2, 3. And then I have hot liquid here and cold liquid here and hot liquid here and cold liquid here. If I think about the area over which the heat transfer is taking place, well, that's this, right? So this is the original area. That's the area of the same plate that we had before. But then it's also happening over here too, right? So we have a hot liquid and a cold liquid, but then here we have a hot liquid and a cold liquid. So heat transfer is going to occur through this surface area too, which contributes another A, another effective A. And then we observe that the same thing is going to happen right here. And so if you calculate out what this looks like, we've tripled the effective surface area over which the heat transfer takes place without changing the external geometry of the object, okay? And because we've tripled the surface area, that seems to suggest that we've cut the thermal resistance down by 3 and then enhanced the heat transfer by a factor of 3. And sure, right, this works, but why stop here? I mean, if I could take one, group of a hot-cold chamber and then do this kind of split, why don't I do it to these 2 as well? Why don't I just keep splitting these little chambers into smaller and smaller chambers that are thinner and thinner, such that eventually my design looks like a massive stack of just basically a bunch of plates of metal with hot and cold chambers in between. And there are a couple of reasons that you might not want to do this. And one of those reasons is the fact that manufacturing this becomes more and more difficult. The more and more of this you do. But this still works. Each of these little layers provides an extra A, an extra contribution to the surface area that allows the heat transfer to be enhanced by a significant amount without altering the external geometry of the actual object, right? The limitations come in not as a result of the heat transfer itself, but more as a result of manufacture and fluid mechanics and things which are important for engineering, but not things that we see in the context of heat transfer. okay? Or at least we don't see them in the context of this analysis. And so there's a bunch of other things that we could do here, right? So rather than having these be straight, we can make them wiggle a little bit. And we can make them wiggle because, of course, the fact that this thing wiggles around increases the surface area by a small amount. And we can also, if we wanted to, carve this thing up vertically. And then we wouldn't necessarily have this kind of like, you know, vertical hot cold, but now you'd start to see cells where, you know, maybe this is hot and this is cold, and this is hot and this is cold, and this is hot and cold. And you can see how the geometry starts to get more and more and more complex. But you can also see that the heat transfer starts getting more and more efficient. All right, and if we take a look at the heat exchanger that I brought in, that I showed you at the beginning of this lecture, surprise, surprise, although it's kind of difficult to get the focus right, you can see that the insides of this thing are extraordinarily complex. It's got that waviness in those horizontal chambers that we talked about. And you can see it vertically. They're also vertical too, just not as often. Let me see if I can show you here. So you can see that there's this kind of like interesting little honeycomb pattern on the inside, which stems from the idea that you're trying to maximize the surface area of interaction, right, over which the heat transfer takes place between the hot and the cold liquid. And so designing this stuff is not easy, and just this simple fact leads to extraordinarily complex and interesting designs. And this isn't the only thing that shows this goofy little design principle, right? Because you can imagine that whenever you have a separating element between two different objects, you can always make the boundary between them more and more complex in order to increase the surface area. This doesn't just show up here, it shows up in other things. Have you ever considered, for example, why a waffle is shaped the way that it is? That interesting little kind of groove structure is the wiggle that's designed to transfer heat from, you know, the waffle press or whatever you call it, to the actual waffle batter in the most effective way possible. And so waffles cook much quicker and much more evenly than, say, like a pancake because of the shape, right? They're optimally designed for heat transfer in that way. You can also see, for example, the way that a CPU heatsink is shaped. You see that most of the time whenever you have, you know, a big CPU, it'll have these like weird little fins stuck on it. And those fins are essentially supposed to be just a way to add more complexity, to add more surface area to the boundary between the CPU and the air, so that heat transfer that occurs between the CPU and the air is optimized. And so once you start seeing this kind of physical principle and stuff that's designed for heat transfer, you kind of never stop seeing it. And so I encourage you to take a look at devices and things that you use very often in your day-to-day life and think about how this idea of making the surface area larger, of making the boundary more complex between two objects, how that factors into the design of things that are well created to enhance heat transfer. One last example, if you have one of those old-timey radiators, you know that it has that very kind of weird winding tube structure. Now you know why, right? It enhances the surface area of contact between the actual device, right, the hot liquid that's going through your radiator, and the environment. So anyways, we'll talk a little bit more about how we quantify the effectiveness of altering the geometry of a device for this purpose when we start talking about the abstract notion of a fin, which we'll do in the next lecture.